Okay, hello everybody. This is a quick example in order to help you with exercise 3 of assignment lab 3. Be aware this is not the same exercise as has been given in the lab documents. It's just one to help you along with it, because you should really figure that one out for yourself, and you need to think about it a little bit so that for that you can use this example. In this example, it's really similar. We've created a graph that looks pretty much like the one that you got in your exercise. We have the same period as well. We use a period of 1, and the signal has the value of -3 from 0 to half its period, then 1 from half its period to 3/4 of its period, and then again -3 for the end till the end of its period. Let's start off by noticing that this signal is periodic. That's the whole idea of this exercise as well. It means that after this period, it will of course continue in the same manner as we see here. So I've a dotted line here which shows that, and we're going to use that fact as well. So we are going to calculate the Fourier coefficients. These Fourier coefficients are used in order to describe the signal that we have here, for example, with the use of other sinusoid signals. These sinusoid signals build this signal together. So let's start off. I think it's mostly the calculus where people ran into, so let's take a look at it. We just fill in the formula. This is the formula that's also in your lab exercises and in the slides and in the documents. So we're just going to fill it in. However, we're going to make a very slight adjustment. So the integral is over 1 period, and we're still going to do that. However, we're going to slightly shift which part of the signal we're going to integrate over. So we're still going to take 1 period, but instead of going from -3 to 1 to -3 over the period from 0 to 1, this is 1 because that's the period we defined. We're going to take the integral from half to 1.5. And why are we going to do that? Well, because if you do it that way, then we only get 2 integrals to start off with. So because this function is discrete, it's not continuous, we cannot integrate in one go. We have to split up the integral. Normally, if you just take from 0 to 1 period, you will have to split it up in 3 parts. This is also the case for your assignment, of course. You have the first one that's -1, then you have the one that's 2, and then you again have an integral with -1. However, if we take the integral from half to 1.5, we can just use 2 integrals as is shown here. Before we carry on, another tip that makes things a lot easier is to substitute some of this information by just one variable. So -j 2pi over t, it's something, times k is something that we not use or change during first few steps here. So we're just going to substitute it with c to make things easier. This looks a lot nicer to work with than this information here that you have to write down every time you make a new step in order to keep it clear for yourself. So we simply fill in the formula. There's not much to add here. You just fill in the formula, you split it up from in the parts we see here. This is 3/4. In the parts that we see here, and you fill in the equation. So yeah, this is very straightforward. Then you just use a basic calculus. You integrate them. So, well, this is something you should all know. This is still pretty straightforward. Then at a certain point, we're going to elaborate. We're going to calculate these components. So we fill in those values, and we get to this part here. And I think This part here is the part where some tips and tricks could come in nicely for you guys. So yeah, we substitute the c back because we can we need those pi values now. This means that for the first value here on the front, also be aware quickly that this 1 over c, we can just take it out, right? We can take it out of these equations immediately because these have nothing to do with the t value for which we're going to substitute these period values here, 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 and here. So we take it out, we put it in the front, we see that we have the fundamental frequency in there, which we this is how we defined it earlier, and we see that the period drops away immediately because, well, the frequency times the period is equal to 1. So this happens at this part here, but it will also happen up in these parts here. So this you can all calculate for yourself, of course, and you will find out these values, and these values can be improved. This part, you might think, well, I'm going to put this into MATLAB, it will calculate the rest for me, there's no need to improve this. Well, you might be kind of right. However, this can look a lot more neat, and it's important that you understand the steps that I'm about to go. I'm going to make in order to make it more neat. So first of all, this value can just be added because those are the same, right? So we get the 4 times e to the power minus j 1.5 pi times k. And then we have this and this value, which can't immediately be added if you just look at them like that. However, this part here we can change it. It's e to the power minus j times 3 pi times k. Well, k is an integer. We can split this up, this exponent up. Also, there should be a k here. And we see that one of the exponents that we have here is actually a component which is always equal to 1. So if we can actually rewrite it like this, and in this way we see, okay, this is equal to 1 to the power k, which is equal to 1. So this is always 1, which means that this is the same as this, is the same as this. So we can substitute this for this, and we see that these two are then the same, so we can add them up as well, and we get minus 4 e to the power minus j pi times k. When we take the 4 out, we'll slightly improve this one as well, since we like to work within the minus pi to pi boundaries. We can just take off 2 pi k, or add 2 pi k, I must say, which transforms this into this, where we have a positive j half pi k exponent. After we've done that, we can do the same trick as we did here. We just take the k out of the power here, and we see again that we have two values that should be quite well known. If you see them, you should recognize those. It's just j and minus 1. So we actually have j to the power k and minus 1 to the power k. So if you put it a little bit more nicely here in this function, then we get this as a result. So this is the result. However, notice that this will only work for k is not equal to 0, because if you put in k 0, then you will go and divide by 0, which is of course impossible. It's good to know, and maybe you might be asking yourself, well, how do I calculate k 0? Well, let's go a little bit back to the fundamentals. The whole idea of these alpha of k's are values, magnitudes that decide how large the impact is of a sign in your total signal when you add them all together. So For example, you have a fundamental frequency, and k times that fundamental frequency means is the frequency of the signal, and then alpha of k is the magnitude of that signal. It means that if you have k is 0, we're talking about the DC, because 0 times fundamental frequency is 0. This is the DC. So the DC you can find yourself actually quite easy in these exercises, because you can just almost see it. And you can very easily calculate it just by using the values that we see here. So it's, for example, this was useful, minus 3 times TO over 2 plus 1 times TO over 4 plus, again, minus 3 times TO over 4. And this will then give you the DC value, which is in this case is minus 6, minus 9, plus minus 8, minus 8. So it's minus 2. Should alpha 0 be then. Okay. Well, then comes the visualization part. If you've done it correctly, then you can also see this back in your formula, because the whole idea is if you use more k's, more sinoids, then you will get a better representation of your signal. So if you could use infinite amount of sinoids, then you can exactly represent your signal. So you can make every signal in that kind of way. So this is a figure I plotted from this exercise, from this example, in which we only use 1k, and this for this one we use 2 Fourier, 4 sinusoids, and here we use 10, and this is for 100, and this is for 1,000,000. So you see, if you use more, you will get closer and closer to the answer. Okay, so that's it. I hope it was a little bit clear. If it's not, then just try it out with the other exercise. Take a good look at this and see if you can work it out. Good luck anyways.